Now let's begin to talk about magnetism. And in many ways, this may seem like a large departure from what we've done with electrostatics and electricity, but very quickly we'll see how very closely they are related. But for now, this is more of just a brief introduction to magnetism, especially with regard to magnetic fields and forces. Now, let's start by thinking about magnetism and magnets themselves, and try to imagine different types of magnets that we are familiar with. And so, the most obvious one you probably have near you right now is a fridge magnet, right? So this is actually a fairly strong fridge magnet right here, and we know that the magnet itself has a magnetic force to this knife, for example. And other types of magnets that are well known to you, you can think of the magnet inside of a compass. Of course, that magnet is going to follow the magnetic field produced by the Earth itself. The Earth is a giant magnet itself. There are naturally occurring magnets. There's electromagnets. Certainly we're familiar with those as well. And so we do find materials that that show magnetic properties, as well as artificially ways of making magnetism throughout our lives. And so we're going to try to divide some of these types of magnets up so we can understand them a little bit better. There's the mineral called a magnetite. And so these are naturally occurring permanent magnets. There are other types of objects that can demonstrate magnetic properties, but the magnetism in them needs to be induced, and it can be taken away as well. And those types of objects are called ferromagnets. And you'll see the name itself, ferro, is Latin for iron, I believe. And so objects that acquire magnetism if brought into contact with a magnetic field. All right, so in some ways, you're inducing magnetic properties onto some kind of object. And then finally, the type of magnet that we're very, very familiar with as far as technology goes, and that's the electromagnet. And electromagnets are simply caused by charges moving through a conductor. And you're saying to yourself right now, I think a conductor, you mean like a wire? Yeah, absolutely, like a wire. When you've got charges moving in a wire, what you're talking about is electricity. And fundamentally, there is a natural magnetism produced by that. And so we're going to look into that very carefully as well. But before we do that, let's take a step back and look at naturally occurring magnets a little bit. And specifically, we can look at a bar magnet. Everyone has seen a bar magnet before. Let me give it a bit of a drawing here. And the fundamental characteristic of the bar magnet is not just that it displays magnetic properties, and therefore can attract and, as we'll see later on, repel. But then it has two polarities. The bar magnet itself is not one type of magnet. It has both types of magnets on it. And in fact, this is how all naturally occurring magnets occur. You can find a magnetite and it will have both a north and a south property. Now, if we take this object right here, we can try to separate it into its two poles. And so let's cut it exactly in half. Maybe we'll take a laser and we'll do a precise job. And we are left with the north side and the south side. And so what we've done is separated these, correct? Well, no. In fact, what you've done is you've basically created two smaller magnets, because what is going to fundamentally happen, let me color this side in. Oftentimes you'll see these bar magnets, they'll be red on one side and white on the other. And so if I've cut a bar magnet into two pieces, what we very quickly realize is that each of the two pieces starts to display the exact same property of its parent magnet. It will have a north and a south, a plus and a minus, whatever you want to call it, two opposite polarities of magnetism. And so you're saying for yourself, okay, let's cut it even smaller. In fact, why don't we try to smash our magnetic field into as small pieces as we possibly can. And so instead of cutting it, let's smash it. Let's take a hammer and we'll just start hitting these pieces until we're left with as small pieces as we can possibly handle. And so we end up with little fragments like this. And we examine them and we measure their properties and we ask ourselves, okay, which of these is north and which of these is south? Which is showing one polarity and which is showing the other? And again, they're both showing both polarities. There's a north and a south on all of these. No matter how small you go, no matter how small we've gone, we have not been able to separate magnetic polarities. Basically, what we would call a monopole doesn't exist for magnetism. The naturally occurring property of a magnetic material is to exist as a pair of poles, which is what is called a dipole. So magnets only exist as pairs. Of poles. And this is what's called a dipole. It's a naturally occurring dipole. Now, very quickly, if we think back to when we talked about not magnetic properties, but electric properties, well, the naturally occurring unit of measure for an electric property was a monopole. It was just a positive charge or a negative charge. This, on the other hand, we can't seem to separate into an individual polarity like we could with the electric stuff. So, for example, an electron is a monopole, but there are no magnetic monopoles. Unlike electric monopoles. Okay, so that gives us just a very, very brief introduction. And naturally what we'd want to do now is to start to talk about properties that will help us to calculate and measure magnetism. And the natural thing that you're probably thinking of is force. We talk about magnets, we often talk about the magnetic force between them. So we have two magnets right here, and there's a force that's keeping them apart. When I try to put them together, that doesn't allow me to do that. There's a force that's a characteristic of that, and we're comfortable with forces. And so just as for the electric charge, when we learned about electric charges, we learned about electric force, we eventually go to electric fields. But this time we're not going to do that. We're actually going to start with the magnetic field, because I hope by now what you realized after studying the electric charges is that it's the field that's more fundamental. The electric field is the more fundamental property of charges, and it's only when another charge comes into that field that a force is produced. We're going to take that same point of view, but now we also have a better understanding of fields in general. Now that we've seen the electric field, I'm comfortable starting with the magnetic field produced by magnetic objects, and then working our way to the forces that are felt by objects experiencing that magnetic field. And so, what are some properties of the magnetic field given by the capital letter B? We use capital E for electric field. We're using capital B for magnetic field. And please note, of course, just like the electric field, that is a vector. So let's try to imagine the magnetic field surrounding a material that has magnetic properties. And you could probably imagine this better than you did the electric field. But I do have a quick video that we can look at in case your imagination is insufficient. Okay, so in this field here, in this video here, we have a couple of students that are demonstrating what magnetic fields look like. What they've done is they take a white piece of paper, then they put a container with a bunch of iron filings above it, and so these tiny little specks of iron dust almost. They mixed it up, but now they put a magnet on top of it. And those iron bits are able to follow the magnetic field lines that are there because of this bar magnet. And so the bar magnet has two poles to it, and what we start to see is lines. We see the iron bits starting to produce lines and giving us a pattern. It's not super clear in this video. We're going to draw it in a second, but you certainly see those lines being produced there, especially there in the center. You can see that line and the curvature of it. Oh, yeah, check out there right at the bottom. Get a good sense of what that looks like. All right, so jumping back into our notes, let's draw the magnetic field of that same object. So we've got ourselves a bar magnet. Maybe I'll just make it that big. And I'm going to have a north end, and I'm going to have a south end. And the magnetic field lines coming off of our object are going to have a pattern similar to what we saw there. And so allow me to draw them. If I've got a magnetic field line, it's going to curve from the north to the south. And we draw it like that. Similar one over here. And so this is demonstrating the direction of that magnetic field at various points. Now, more complicated than the electric field of a single charge, I would say, but not overly so. And we'll throw some more in there, but we won't show all the details for space purposes. So all of our magnetic field lines are coming off of our north, and they are going into our south. Like so. All right, and so what we have here is a pattern that we saw produced by the magnetic field from that bar magnet in the video. But you start to wonder what happens in between, like what happens within the magnet itself. Well, what we actually understand is that these magnetic field lines, I'm drawing them dotted here because this is within the magnet itself, close around each other. So these magnetic field lines are actually loops that are continuous loops. And so this one here would go up there, this one would go like this, and they're basically straight lines of magnetic fields within our object. And they close those loops as full circles. That's pretty good right there. All right, so this is an interesting pattern, more complex than a single charge and the electric field surrounding it, but actually exactly the same as if I would have two charges that were separated by some distance. So what do I mean by that? I mean, even though an electric charge's natural state is that of a monopole, it's super easy to create a dipole. Take a positive charge here, take a negative charge here, fix their distances so that they don't go colliding into one another. And what you have in this case is the exact same shape. Field produced by the two. I won't draw the one for our electric field, but basically this one would have the exact same shape as that one over there. Okay, so we've got an idea about this magnetic field for naturally occurring objects, but very quickly what we're going to learn is that we're not really as interested in talking about the properties of the magnetites or the ferromagnets as much as we are at looking at electromagnetism, how the electric charges moving in a conductor could somehow create a magnetic field. Well, that's something that was relatively recently discovered in the course of science history, and it was done through something called the Oersted experiment. Interesting story behind that. I won't get into too much, but I recommend maybe looking it up if you're interested, is that this property of magnetism was actually discovered during a physics lecture. And so what the lecturer had, Oersted, was a battery. And that battery had a wire connected to it, like so. And it was placed like that, and consider this to be the workbench at the front of the lecture hall, etc. And Oersted also had a compass nearby. And that compass was, of course, pointing towards north. It was calibrated correctly, and it was following the electric field created by the Earth. Now you'll notice one thing is that this is not connected. And so right now what you have is a wire that has electrons within it, but those electrons are not flowing. And when they're not flowing, Well, the magnetic field of the Earth is the dominant force here. But something very interesting happened as soon as Ørsted ended up connecting the wire and closing the circuit. Well, once Ørsted closes the circuit, what you end up having is a flow of electrons. And so charges begin to flow once we close it like that. And what he noticed was that the compass deflected. And the compass deflected specifically in this direction. And so we have our current going through the wire, and as the current goes through the wire, those electric charges are moving around, and when they do that, there is a magnetic field produced. And that magnetic field is being felt by our compass, is being measured by our compass. It is in fact stronger than the Earth's magnetic field at that point. And so what Ørsted discovered in this experiment is that current creates a magnetic field. And so don't forget about all of the electrical work that you've done up until this point. It's going to be important for us when we study the electromagnetic properties of current carrying wires. Creates a magnetic field. All right, so there we go. We have our discovery of the magnetic field with relationship to moving charges. And naturally, the next thing we want to do is to talk about the strength of the magnetic field as well as the direction of the magnetic field that is produced by these current-carrying wires or even just random charges. Okay, so now we're getting deeper into magnetic fields, and it's about time we learn about how to calculate the magnitude of magnetic fields produced, as well as the direction of those magnetic fields. And so I think I'd actually like to start with direction. And what we'll do is to determine the direction of the magnetic field produced by a current-carrying wire. There will be other methods by which we will be able to figure out the direction of magnetic fields. This is one way to do it, and this does work for wires. It's not useful for individual charges that are moving around. They also create magnetic fields, but it does work for a wire. And this method is known as Ampere's right-hand rule, or Ampere's right-hand rule, I think is the correct pronunciation. And so all you basically have to do, you've got this wire right here, for example. If there was current going through this wire, you take your right hand, so this is Ampere's right-hand rule, you can only use your right hand here, and you use your thumb as the direction of the current. So for example, if you knew the current was going upwards here, you can point your thumb upwards and you grasp the wire with your fingers. And the direction of your fingers, as if there's little arrows coming out of your fingers, is the direction of the magnetic field produced by the wire. So if it was going, let's do a different one. Let's say it was going to, well, it's hard to hold sideways. Hopefully you can see that. Let's pretend that it's going in that direction over there. Then we make our thumb in that direction and we wrap our fingers around it. So the magnetic field produced by that wire is going around the wire like this. Okay, let's write some of that stuff down and then we'll do a couple of quick examples to make sure we're good at finding the direction. So to determine the direction of the magnetic field, Again, don't forget that's given by the capital letter B, produced by a current-carrying wire we're going to use Ampere's right-hand rule. All right, and so the right-hand rule is exactly what we said it is. Use your right hand, you grasp the wire with your thumb pointing in the direction of the current, and that means your fingers are the direction of the magnetic field. So just to make sure we all got it, that's a crazy looking G. Let's grasp the wire with your right hand, and then with your thumb pointed in the direction of current. Really, there's only two ways to grasp a wire, right? You're either going to grasp it this way or you're going to grasp it that way. You just make sure your thumb is pointed in the direction of the current. All right. And so step 2 is really just look at your fingers, or to be a little more scientific, let's say that the B field direction is the same direction as your curled fingers. All right, and so it might seem pretty straightforward if you actually had a wire to figure out which way the magnetic field was going, but oftentimes you're going to be evaluated by a wire on a piece of paper, and so you have to be able to tell the direction of the magnetic field by looking at a drawing of the wire. And so before we get any practice with that, we need to be able to tell directions that are coming out of the page and going into the page as well. And so I'm going to give you these two directions that are commonly used when we're talking about magnetic fields. And the first one there is a circle with a dot in it. That one is just the direction out of the page. The other one is a circle with an X in it, and this is a direction into the page. And that'll give us a lot more versatility in doing directions on a piece of paper, right? Obviously we've got up and down and left and right, and now we've got in and out as well, given by those terms. A really quick way to make sure you do remember which is which, the vector can be thought of as an arrow. So imagine that when we have a direction that's coming out of the page, it looks like a circle with a dot in it, or you could think about it as if there was an arrow that was like coming towards you right before it hits you in the face. It looks like essentially like a circle with a dot in it. That's what the sharp bit of the arrow would look like. On the other hand, if you yourself were to shoot an arrow, as it goes away from you, it would look, the feathers on the back would look like this X moving away from you. And so that way you can think about, coming out of the page or going into the page. All right, great. So let's try a couple of examples of just figuring out the direction of these magnetic fields due to the current. Let's start nice and easy. Let's say that that is our current. And so what we have here is a current coming out of the page. It's headed towards your eye. And so I want you to try to calculate the direction of that magnetic field. And so using our Ampere's right-hand rule once again, I can do it here. Let's see, the thumb is coming out of the page, and then my curly fingers are the direction of the magnetic field. It doesn't say where we want the magnetic field, and so we basically have to draw it everywhere. The magnetic field for this one, let's say the question is simply, what is the B field direction? We can draw it around this in the following way. And it is headed this way. And please check that for yourself right now. Make sure that you agree with that. And you don't have to hold it up and do it to the screen the way that I've done it. I mean, eventually you're going to be probably writing a test, and you're going to want to be able to do it on your own piece of paper, on your own problem. And so hold your paper or keep your paper down on your desk like this. Have your thumb go in the direction of the current, and then you could see that your fingers are pointed in a counterclockwise direction. That's the answer here, counterclockwise. What is the magnetic field direction? Counterclockwise. All right, let's try something different, but using a similar skill. Now that we've done that one, I actually want you to try this one yourself, so feel free to pause it once I give you the question. Say we've got ourselves a current going into the page here, and this time I'm going to ask you for the magnetic field at a very specific spot, okay? Why don't you find me the electric field right there at this point P? So again, what is the magnetic field direction? So I'll give you a second to give it a try yourself, and then we'll take it up. And so once again, we take our right hand here. This time it's going into the page. And so we point ourselves into the page. With our thumb in the page, we can curl it around and see which way it's pointing. Well, if you look at it, it's going clockwise. But I'm not asking for the overall direction around it. I want the direction at P specifically. So it's going into the page. Our magnetic field is going around like this, but at this point, to the left of it, it's actually tangent straight up. And so if we want, we can draw the full magnetic field, but that's not what the question is asking. So yes, there's a magnetic field surrounding this spot. It is headed in the clockwise direction, but at the point P, the direction of the magnetic field is exactly tangent to that circle. And so that means it is a tangent in the same direction, and right there it is going up. The correct answer is up. Finally, let's try one more, a little bit different still. This time we're going to take a wire. That's not good. There we go. And we'll run a current through this wire. It's going all through the wire in that direction. I want to know the magnetic field specifically at the point P, which is over here. And the question once again is the same. the magnetic field direction at P. I should write that up there as well. The magnetic field direction at P. That's what we're looking for here. All right, so give it a pause. Give yourself a second to try to figure out what it is, and we'll come back and take it up. So here we go. We've got our wire, the electric field, or sorry, the current is going in that direction, so my thumb is kind of going that way, sort of diagonal, but it doesn't really matter if it was horizontal or diagonal. What we know is that the point is underneath the wire. And so if my thumb is headed this way, my electric or my magnetic field is curled around. It's curled around until it ends up underneath. And underneath, it's going into the page. The correct answer is into the page. Give that a practice. Make sure you can use Ampere's right-hand rule. Or you can just write it like this. That's good. Let's do it a little neater. There we go. So now let's try to calculate the magnitude of the magnetic field created by our current-carrying wire. But before we do that, we have to think about what is current-carrying wire. It's just charges moving around. And so let's get even more basic than dealing with the current-carrying wire and just figure out what the magnetic field is due to a single charge. What about a single point charge? A single point charge has an electric field associated with it. Does a charge have a magnetic field associated with it as well? The answer is yes, it does. And the calculation that we're going to use to find out what the size of that magnetic field is called the Biot-Savart Law. That's the Biot-Savart Law. And there's two types. There's one for wires, but the one we'll look at first is that for point charges. By understanding this, we'll be able to understand the Biot-Savart Law for wires a lot better. I'm going to go ahead and I'm going to write this down, and then we'll kind of analyze it a little bit. So the magnetic field for a point charge is given by the following equation. Mu naught divided by 4 pi, all multiplied by Q, V cross R hat, divided by R squared. Okay. That is a very complex looking equation. But if we break it down, it actually has a lot of similarities to an equation that we know very well and, dare I say, love, well, some of us anyway. Recall the equation for the electric field, also due to a point charge. You know it as kq over r squared. If we write it in its other form, it's 1 over 4 pi epsilon naught q divided by r squared r hat. Remember, the r hat is a unit vector. It gives us the directional information we need, but the size of the unit vector is just 1 when we're finding magnitude. All right, so that is sort of the longer version of our electric field equation. I want you to compare both of those equations together and come up with some understanding of what the different terms are. So let's start with this term right here, and both of those are constants. They're both 1 over 4 pi. The epsilon naught is a constant for our electric field, but the mu naught is a new one that is specifically for magnetism, and this one is called permeability. And so we will learn its value in one quick second, but basically what we know is that 1 is the constant with regard to electric field, and the other one is for magnetism. All right, let's look at the next term. We've got a Q here and a Q here, obviously equivalent. This is the point charge, the charge of our value. So the only sort of characteristic of the charge that seems to matter for the electric field is just how big the charge is and how far away you are from the charge. Because they both have Q and they both have R squared, right? The distance to the charge is going to determine the strength of both the magnetic field and the electric field. So where's the real difference between them? It's really this V term, right? Here we have V cross R hat. Here we just have R hat. Where V here is velocity. It's the velocity of the charge. So what happens if our point charge has no velocity? Then it has no magnetic field. If you take a point charge and it's not moving, it has no magnetic field. It still has an electric field. But if you then move that charge, the electric field doesn't change. It still has the same amount of electric field at a given distance r, but its velocity alters the magnetic field. The faster it goes, the stronger the magnetic field. All right. The other thing that this equation has that can create a little bit of confusion is it has a cross product. And so we want to do a very, very quick review of cross product because it's going to be super important going forward. You are expected to know cross product. If you need more information than this, please review your mathematics for the cross product. But very, very quickly, if I had two vectors, let's say A vector and C vector, staying away from the letter B for magnetism, of course, and I wanted to calculate the magnitude of that cross product, not the direction right now, and it does have a direction. When we have a cross product, the answer to the cross product is also a vector. That's different in dot product, but for cross product, you do have a vector, so a magnitude and a direction for your final answer. But focusing just on the magnitude, if I have a vector, I can take its magnitude and multiply it by my C vector magnitude, and then I multiply by the sine of the angle between them. Sine of the angle between A and C. And so you can just write this simply as A times C times sine of theta. Pretty good. But notice that our equation here that we're going to be using in just 1 second is V cross R hat, V cross R hat. Now if we have V cross R hat, then we have to be able to deal with the unit vector. Unit vector actually makes it easier. So let's see what happens if we take the cross product of a random vector with a random cross product. Well, we do the same thing. We take the magnitude of the first, multiply by the magnitude of the second, times sine of the angle between it. So what's the difference here? Well, what's the magnitude of a unit vector? If you recall, a unit vector is a vector that has a direction, but whose magnitude is always just 1. And so that term goes to 1. And we're left with a sine of theta. All right. So there we go. That'll help us deal with the equation. And so as a quick example, if I had, let's say, a positive charge here, and it had a direction here, V, and since V is a new term here, let me just write this is the velocity of our charge. Let's say for a second that our point is located over here, P. We're going to need this distance R, and we can try to use our point charge to find the magnetic field using the equation mu naught over 4 pi multiplied by Q V cross R hat over R squared. Now clearly that, once we look for the magnitude, becomes mu naught over 4 pi. That's a constant. Q, the charge of my charge Q, I have that. And then instead of V cross R hat, I actually have V sine of theta, where theta is the angle between V and R hat. I don't see R hat there. I know what R is. What's R hat? Well, R hat is going to be the directional vector from our charge towards P. It has a size of 1, but it has a direction such that it points towards the point we're trying to find the magnetic field. And so the angle between those two is theta. And so if we have all of those values, we can use it to calculate the magnetic field B at that point. And I guess the only value I didn't give you is mu naught. So let's fill that in right now. So we know what all of these terms are. We have V as the velocity of the charge. And there we have mu naught equals 4 pi times 10 to the negative 7 Tesla meters per amps. Now we haven't talked about the SI units of magnetic field yet, and so we should do that as well. But this term is known as the permeability. There we go. And let's add the units to this. Are measured in Tesla, named after Nikola Tesla and the great contribution that he did towards understanding of AC circuits, and we will get to that a little bit later. The one thing that we do want to do is figure out the direction of the magnetic field. We can use this equation to calculate the magnitude of the magnetic field, but we are going to need something else to calculate which way the magnetic field is pointing in a problem like this. We can't use Ampere's right-hand rule. We instead have to use what's called the general right-hand rule for cross products. Okay, this general right-hand rule for cross products is going to make use of 3 parts of our right hand. So we still use our right hand. We're going to use our 4 fingers as our first direction. Our second direction is going to be our palm, as if there was a vector coming out of the palm, right? Almost like you're shooting an arrow out of your palm. And then our third direction will be represented by our thumb, and your thumb has to be 90 degrees away from your fingers. So make sure you can do that. Everyone, get some good stretching exercises in to make sure we got a good 90 degrees right there. And so the direction of these 3 sort of things is how we're going to determine the general right-hand rule. So let's dive right in. So, step 1, put your fingers in the direction of the vector in front of the cross. So whatever vector you have in front of the cross, in this case it is V for velocity, your fingers go in the direction of that vector. Now I'm not saying V here just because we will be using this right-hand rule for other equations as well, so we're learning it in general. Second is to put your palm in the direction of the vector after the cross. All right. So you put your fingers in one direction, you put your palm in another direction, and then finally you move your thumb so that it's 90 degrees away from your finger. And that will get you your answer. And specifically the direction of your answer. Now, step 2, we talked about your palm. That was the part after the cross when we were talking about the Biot-Savart Law specifically. That means R hat. So R hat should point in the direction of, or your palm should point in the direction of R hat. And that means our thumb is going to be in the direction of the magnetic field, finally. All right, the only exception to this is if you're doing this for the Biot-Savart Law specifically, and the charge is a negative. Then you flip your final answer, your thumb, 180 degrees. All right, there we go. So it takes a little while to get used to. You're going to need lots and lots of practice. But basically, you put your fingers in the direction of the vector in front of the cross, your palm in the direction of the vector after the cross, and then you extend your thumb to 90 degrees, giving you the answer that you're looking for. Okay, so let's do a couple of examples. Let's say that we have a Biot-Savart problem where we've got a plus charge here. It has a velocity in this direction, obviously downwards, and the point that we care about is P, located over here. And the question is, what is the direction of the magnetic field at P? Well, we go back to our right-hand rule, and specifically we go and look at our equation that we have with the cross product. This is it here. And you don't really care about any of this stuff here. It's really just, it's really just the V cross R hat is equal to B that we need for the right-hand rule. Our fingers will be the direction of V. Our palm will be the direction of R hat. And then our thumb will be B. Let's see how it goes. This one we're all doing together. And we start with V for velocity. Okay, so looks like our fingers are pointing down. That seems great. Now our point P is towards the right. We always have to have our R hat going from the charge towards P. And so we rotate it around like this. So there we go right here. And as if we had an arrow coming off of our palm towards our point, and then we extend our thumb. And the thumb is pointing out of the page. That's a correct answer there. All right, let's give one more, and I'd like you to try this one by pausing the video and giving it a shot. And don't worry, there'll be lots and lots of more opportunity for you to try these problems. Let's say I've got myself, this time, a negative charge. We're going to have our point here, P. And I'm actually going to have my velocity go into the page. Like so. So that negative charge is actually going into the page. That's the direction of its velocity. And so once again, what is the direction of B at P? Pause it and try it for yourself. Okay, you're back. And so again, we have our fingers in the direction of what's before the cross. That's V. So it's going into the page. So like this. This is hard for me to do from your point of view. I'm not doing it for my paper. I'm doing it for you. So just like your fingers now should be pointing into your computer screen, mine are pointing this way. And then I'm going to rotate my hand so that my, oh my gosh, I'm going to break my arm. Let's go the other way. Our fingers are pointing into the screen. Our palm is pointing towards P. And then we extend our finger and our thumb and it's pointing up. And so the correct answer is up, right? No, that's incorrect because it's a negative charge. And so we have to flip the direction of our magnetic field 180 degrees. All right, there I did break my arm. And so the correct answer is down. Okay, so now that we've got our first sort of theory and equations on how to calculate the magnetic field due to a electric point charge or a point of charge, let's practice a little bit. And we'll practice with this question right here. We've got ourselves a proton. It's moving along the x-axis in the positive direction with a velocity that's given. Just as it passes the origin, find the magnetic field at a position given of x equals 1 millimeter, y equals 1 millimeter as well. And there should be a drawing with this, just to demonstrate what's happening. Consider this part of the question. We've got ourselves a positive charge, and it is moving in this direction. It was given in the positive x direction. Let's put our charge right at the origin of our xy axes. Help us to get an idea of what's happening. Now the point that we're looking at to find the magnetic field is x equals 1 millimeter, y equals 1 millimeter. So we'll put it about here. Call that P, and we're looking for B at that point. All right, so that looks good. A couple of constants we're going to need to solve this. We have a proton. The charge of a proton is positive 1.60 times 10 to the negative 19 coulombs. And we've got our mu naught, which is our permeability. Permeability is 4 pi times 10 to the negative 7. These are SI units, Tesla meters per amp. And that's it. Let's jump in and try to solve this problem. I think I'm going to draw a little bit more on here as part of my solution. And so I'll just cut and paste it over here so it doesn't mess with the question. But basically to do this problem, I'm going to need my Biot-Savart Law. The Biot-Savart Law is the only way I know how to solve this problem. And it is written as mu naught over 4 pi, constant. It's a bit of a strange looking mu naught. Let me make that a bit clearer. That's good. Is it good? It's not great. Let me try one more time. There we go. And we've got our Q, that's our charge, V, our velocity, we're given that, cross r hat all over r squared. Okay, so we have two steps in this problem. The more difficult is to find the actual magnitude of the magnetic field, and then the other part will be to find its direction. And so the only thing I want to add to my diagram here is r, that this distance here is little r, and that this vector here is our r hat. And that angle there will be theta, which we will need as soon as we take our equation and do the magnitude of it. So that's the B vector equation. Just to get the magnitude, we have mu naught over 4 pi QV sine of theta, all divided by r squared. Okay, no algebra necessary for this problem. We're looking for b. We have our equation in terms of b. Let's make sure we have all of the various details. We have mu naught and q as given. R is less known. So what is r in this problem? Well, if this location here is 1 millimeter by 1 millimeter, we can do a Pythagoras theorem to figure it out. So this is 1 times 10 to the negative 3 meters, x position, and 1 times 10 to the negative 3 meters, y position. So to get the distance, it's just the hypotenuse of that triangle. If you don't see the triangle, just to highlight it, it's this one right here. And so our R position will be given by 0.001 squared plus 0.001 squared, all rooted. And throw that into our calculators to get the hypotenuse of the triangle, which will be, in fact, we won't even bother finding r. We can find r squared instead, since that's what's in the equation, and it's a lot simpler because it's just 2 times 10 to the negative 6. And so let's throw everything in. Velocity was the last one. Yeah, velocity was given as well as 1.0 times 10 to the minus 7 meters per second. That's right out of the question. And then finally, theta. Before we go too far, we need to find what our theta value is, and theta is the angle between the two. And since you have a position of 1 times 10 to the negative 3 and 1 times 10 to the negative 3, you know that that's 45 degrees away. This angle here has to be 45 degrees because of the location of our point. So we'll just put that here and finish the problem. Let's throw these values in, and I highly, highly recommend that everybody try this right now on your calculators, because sometimes people get messed up with these types of problems. For example, with the 4 pi's. So you've got your 4 pi's disappearing with one another. Make sure you can handle the 1 times 10 to the negative 7 properly on your calculator. You're not doing it the wrong way. So we've got 1.6 times 10 to the minus 19 multiplied by our velocity, 1 times 10 to the 7, sine of 45 degrees, all divided by 2 times 10 to the minus 6. Okay, if at this point you haven't calculated yet, I'd pause the video, make sure you get a value, and then check with me. And while it's paused, why don't you try to calculate what the direction of the magnetic field at P is as well. Okay, putting these numbers into my calculator, looks like we've got 2 sig figs. We have a magnetic field magnitude of 5.7 times 10 to the minus 14. So quite small. That is measured in Tesla. And the last thing we need to do is to calculate the direction of the magnetic field. And so we go ahead and we use our right-hand rule for our cross product. We've got our velocity headed in this direction here. And we've got to try to, oh, this is tough. I might be covering it a bit here. So let's see, our velocity is going this way. And our P is that way. If I curled my fingers towards it, so my palm is, can't quite make it point that way, that's fine. It's basically like this. It's in the general direction. And then our thumb is the most important thing. And it's coming out of the page. So even though R and V are not 90 degrees away from each other, you can still do the right-hand rule. Just make sure your palm is pointed in sort of the quickest way to get to the direction of our hat, leaving us with a direction that is out of the page. There we go.